All right. Well, thanks for just coming back, watching this video. Sorry it took longer to get the files moved over than I wanted last night, and so I didn't get this video made. So what I want to do is come back and describe a scenario that was sort of concocted by David Mermin, and then and it explains Bell's theorem, or something equivalent to Bell's theorem, and it's a really clean result because when you do Bell's theorem, the video when I went through it, you have to do all these probabilities, and you kind of work with these abstract, hypothetical probabilities for hidden variable theories. But since it's all supposed to be general, you're not able to really write down very much that's concrete. And then you kind of manipulate them, and you find that there's some bound that can't be satisfied. And so therefore hidden variables can't exist. And nature is fundamentally non-local, the way Bohr would tell us. Or, well, may or may not be quite like Bohr says, but what it has to be is non-local. So it can't be the sort of picture that Einstein wanted. This other way, this other version of Bell's theorem, it's going to be based on a different state, rather than doing the singlet state and using that to make entangled pairs. We're going to use something called the GHZ state, and I'll explain that in a minute. But before just diving into the math side of it, what I want to do is follow an article. It's really just a beautiful article by David Mermin. I think it's called Quantum Mysteries Revisited. And it does this, it basically presents things kind of like a game. Just says, well, here's what we see, and make all the usual assumptions that humans are kind of have evolved to make about causal effects and things like that, and go through and analyze this game. And this game is actually, turns out, isn't just something made up with fictitious rules. It's really the result of spin experiments. But so I thought I would try to kind of explain that and describe it from the point of view of somebody who hasn't been going through Bra-Ket vectors all summer, and somebody who hasn't been thinking about two-slit experiments and Heisenberg uncertainty principle, things like that. I'm just going to state kind of the setup and the results we see, and then try to make what anyone would think are reasonable assumptions, a la Einstein, Podolsky, and Rosen. And what we'll find is that there's a problem. So that's kind of going to be the upshot. And then I will go through and rewrite this in the language that we're familiar with Bras and Ket vectors, and we'll kind of work out the details. Okay, the GHZ state. I'm sorry, using the GHZ state. Okay, so here's the basic scenario. We imagine, and we now know what's happening here. There's some sort of a crystal or something, probably, I don't know, particles come in, hit the crystal, and stuff flies out, okay? And for whatever reason, it can be arranged so that there's a source, put it right here in the middle, and then there are three observers. Okay, so the observers, they have a little detector box. Okay, and so here's what we know. You push push play. You push the button here on the source, and you're going to get clicks and things happening at these detectors. And so, well, okay, so schematically then, what you would say, or what you would intuit, is that the particles travel something like that. And you could do all sorts of tests. So let me say a little bit more than that. These detectors aren't just yes, no, click or not click. It's a little bit more sophisticated than that. They have some options on there. And what we see is that each one has an option, and I'm going to call it X button or Y button. X or Y. And really, there would also be a Z button if we're thinking about spin, but it's not going to be important for me. So I'll just stick with X and Y. Okay? And what these are buttons, and there's a person here, so let's put Emily, Marie, and Marcus over here. So, all right. And so what happens, and then there's a little screen. Right here. All right? And we'll just assume there's a default state where there's no reading. Okay? So you can imagine, okay, you push the button, and if Emily has pushed X, fine, and then on the screen will appear, first time, say, +1, and then the next time appears -1, and then +1, and then -1, and +1, and -1, +1, -1. And same thing, all these detectors are completely equivalent. They're carbon copies of each other, and you can check in any way you want. They're identical. They seem to all work the same. And what each person sees is that if they push either the X button or the Y button, they just see 50-50. Click, click, there you go. +1, -1, +1, -1, +1, -1. They just see 50-50 random noise, basically. Just up, down, up, down, up, down, up, down. And of course, given all of our previous discussion, what I'm really thinking of here is these are magnets and you're measuring spins of things. But all right, forget all that. Imagine you're explaining this to your grandmother. You have boxes, you have buttons. That's a choice of measuring. For us, I don't mean choice of measuring spin in a certain direction, but it's just a button that chooses something. The experimenter can push and choose X, Y, +1, -1, +1, -1, +1, -1. Marie sees +1, -1, +1, -1, +1, -1. Marcus sees +1, -1, +1, -1. All see +1, -1, 50-50, regardless of what they do with X or Y. And so, if you're giving this away as a gift on Christmas morning as a game to somebody, they'd say, not so interesting. Okay? And now, it's a little more interesting than that, because so everybody makes some choice. They push X or they push Y, fine. They get a result, +1 or -1, fine. And then they think it's all just random noise, just totally random. Well, that's not exactly right. It turns out, and this is what happens in the real system, when they get together and they talk. So you can imagine these are way far apart. One could be on the moon, on Jupiter, and on Pluto. And years later, they come back together and then they compare notes. So they come back and compare. And what they see is that, you know what? Every time they compare, each time somebody pushed the start button, if one of the three, I don't know if that's visible, that may not be visible, do this, the shine. If only one person pushed X and everybody else pushed Y, then it turns out the results are random for each separate piece, but they're not independent. So it's not kind of maximally random. There are correlations between them. And here's what you find. It turns out that if only one person pushes X, then when they compare notes, they see that when you multiply all of the results, you get +1. Multiply them. Okay. So, this is something we have to understand. How could this be? Well, so there's some unknown black box, essentially. We don't know what happens in the source. We don't know anything. Okay. So, let's assume, a la Einstein, Podolsky, Rosen, or you could just say, a la the collective sum total of all human experience before Bohr, Heisenberg, and Pauli and that group. How can this happen? How could this be the case? Well, what you'd say is, well, evidently, it wasn't that you just send particles or send objects down the pipe totally in an uncontrolled fashion, that you must be this source must kind of stamp out and send the particles out in a correlated fashion, so that, basically, shoebox or shoe manufacturers, they don't just put shoes in boxes and send them to the store. They send them out in a correlated fashion, so that you get one of each type. Okay. Well, now this is I guess for a three-legged person or something like that. So evidently they're sending out shoes in triples, and there's some sort of a correlation between the way that they're being sent out. Okay. So okay, fine. So now it's also true though, there doesn't seem to be any pattern according to who gets +1s and -1s, only that the product has to be +1. So you could have plus minus minus, or minus plus plus. No, that wouldn't work. Minus minus plus. But so they're kind of randomly distributed as long as equally, with equal weighting, with this condition being satisfied. Okay. Well, we may not understand how a particular arrangement is obtained. So you might say it's a hidden variable, or describing the dynamics of exactly how each configuration was produced. Maybe we don't know, but we have this result. Okay. So one thing we could do is just enumerate all the ways you can make a machine that would create three particles with 1s and -1s assigned, and sends them out, and we can just enumerate all the possible ways to do that, where if only one person happens to choose X, they all get +1. And I want to emphasize, because these could be way far away, the particles would be created, potentially, long before anyone's actually chosen X or Y. So it could be, you create this on January 1st, and then the particle doesn't reach the detector until, March, I don't know, whatever. And so you have that whole time in between. So you would expect then that the choice that someone will make in the future can't affect the property of the particle produced at the source. Okay, so we would just imagine that you push the play button at the source, particles are sent out with some combination of spins, and then we just have to enumerate all the ways you could do that. All right, so let's do that. So what I'm going to do is kind of imagine, in my mind, I kind of think of it as if the source is controlled by a punch card, a set of instructions. So at each run, each time you push play, one of these punch cards must control how the particles were created. And I'm going to just generally label these as S. S could be plus or minus. So I'm going to put the result for, we're going to put Emily, and we're going to put Marie, and we're going to put Marcus third. Okay? So, and then what we're going to have here is, we're just going to write down if Emily, the result, if in the X or Y, so if Emily pushes X, she gets this number, and if Emily pushes Y, she gets that number. Marie would have the same thing. The same set kind of options or possible results. Right? And now we know that I'm taking S because I want to think of it as a hidden variable for, or some sort of a variable for spin, but really it just could be, it's just something that could be plus or minus 1. All right? So Emily, Marie, Marcus, 1, 2, 3. And top row is X, bottom row is Y. Okay? So how could you create or send, a punch card of instructions for the source to send particles out? We don't have to understand why a set of instructions is chosen, because it's supposed to be a hidden variable. We just want to enumerate what the possible instructions are. Okay, well, let's do the easy one first. Okay, we could have plus, well, they could all be pluses. Okay, so, or plus 1, everything be plus 1. So that would mean, let's look at let's say Emily chose X, Marie chose Y, and Marcus chose Y. You would have plus 1 times plus 1 times plus 1 is plus 1. Or Marie could choose X, and Emily and Marcus could choose Y, and you'd have plus 1 times plus 1. Anyways, any way you multiply them, you're going to get plus 1. That's a good state. Fine. What's another state you could have? You could have the following. Well, if the person choosing X, no matter who it is, gets a plus, then when we multiply the other two Y values, they could both be, you could have two minus signs. So you could do plus 1 times minus 1 times minus 1. So one possible run, so you kind of would look at these little kind of, if Emily chose X and Marcus and Marie chose Y, you look at that combination and you multiply them and get plus 1. If on the other hand, Marie chose X, remember, it's not that, okay, if Marie chose X and Emily and Marcus chose Y, you would look at this combination. And sure enough, they multiply to plus 1 as well. Now, I keep focusing on these situations where only one person chooses X. They wouldn't know, they would all just choose whatever they wanted. But the experimental observation is about the special case where only one person chose X. So that's why I'm focusing on it. And remember, the particles aren't detected until maybe months after they were created. And so you wouldn't expect the choice of a future measurement, a choice made in the future, to affect what happened when the particles were created. So I'm just zeroing in on a subset, I guess, of the experimental runs for which this correlation is supposed to happen and trying to deduce what the options were. All right. Now, are there any other options? Well, let's see. Let's think about this here. What we could have, let's try, let's say Emily chooses X, and she gets plus. And we don't know what she gets in the Y direction, because she measured only in the X direction. And now, what else could we have? Well, you could have, if you're all going to get plus 1, we have to have minus minus there. So what we could have, though, is, let's see, this one up here could be plus, in which case you're going to get back to this one, where they'll all have to be plus. But what you could have is, oh dear, I take that back. I want to do this one right now. I want to do plus plus. What I could have is minus minus, and then a minus here. So let's check that. If Emily chooses plus, then Marie would see plus, Marcus would see plus. That's good. Or we could have Marie see minus, Emily see minus, Marcus see plus. So that would be minus minus plus. That's also a plus 1. Similarly, we could have Marcus getting plus or minus, and then Emily and Marie would, well, in this case, Emily would see minus. And so that would be allowed. So that's a good one. All right. Well, so I usually start these to enumerate them. I kind of starting with the starting by focusing on the person to the left, so Emily, the way I've written it. But everything's fully symmetric, so we must also then have the following: minus plus minus plus minus plus and minus minus plus 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 minus. Okay? So those must be allowed. All right. Are there any other options? Well, there are. There's 3 more, turns out. So let's go back. Let's assume that, I apologize. I'm having all sorts of computer trouble with this one. The video oddly skipped like a 5-minute section where I could finish this example. So I'm going back to recreate that. Okay, so we had these states. The other option would look something like this. You could have plus, plus, minus, 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 or minus, minus, plus, plus, minus, minus, or minus, 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 plus, plus. Okay, it turns out these are the only ways you can produce particles, send them out, and assign pluses and minuses such that if one person measures in the X direction, pushes the X button, and the other 2 people push the Y button, that when you multiply the results, you get plus 1. You can see here, you get plus 1, whatever. They work out. Okay? So that's great. Now, that's it. Local realism. That's all we've assumed. We've just assumed that particles have properties before you measure them, and they carry those properties with them. And that they can't signal to each other when they're separated and far apart from each other. When you look at these set of possibilities, first you just say, well, it's pluses and whatever. But if you look carefully, there's one other thing you can see. Evidently, you would conclude, if this is right, that if every person, all three, measured X, pushed X, look what you get. Plus, 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 minus, 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 plus, minus. What you notice is if all three people pushed X, the product of all three is plus 1. So here we see local realism, or local hidden variables, require that x, x, x produce plus 1. Okay? So, again, only thing that's gone into that is the assumption that the particles carry their properties as with them, and those properties are measured in experiment, and the effect, and the measurement of one particle can have no effect on any other particle. Local realism. Okay, well, when you perform the experiment, this is not what you get. What you find is that x, x, x produces minus 1. You say, so what? Who cares? Weird. Well, it's a big deal, because the only assumption we made was that you had local variables which controlled things. And the act of in measuring 1 didn't somehow change things far away. And in science, we have this trump card. Ultimately, it is whatever experiment says it is. So this is right. Which means this is wrong. These assumptions are wrong. Reality is not local. So what are the options? It can't be local. You can't have local realism. You could have a non-local hidden variable. You could have a situation where the particles carry their properties around with them, blah, 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 and then so each one of these particles would have had a certain value of plus or minus 1, and then when Emily makes her measurement, that somehow flips the signs for Marcus and Marie. That's a logical possibility. But and another option is the quantum mechanical interpretation, where no system, no particle had any attribute until the attribute was measured. And then they all, are then the wave function collapses and they're in a state of definite correlation with experimental outcomes. But that's a non-local thing too, where because the collapse of the wave function, once an experiment was made in one place in the universe, immediately the wave function to describe the system is changed everywhere in the universe. But however you slice it and explain it, both options involve non-locality. And what I would say is, no one knows how to rule out non-local hidden variables, but what I would say is the inspiration, the motivation for all this was Einstein's desire, first of all, his kind of aesthetic value for local realism. Well, evidently that's just too bad. But also relativity, and you must have somehow be good things that need to be good with relativity. The way, at least in part, that happens in the quantum mechanical case is that even though we have non-locality, we can't use that non-locality to send messages. Each person separately just sees pluses and minus 1s. It's only after the fact, when they do normal, everyday, classical communication, that they see these effects. Emily, by herself, only sees what she sees. She can't tell if Marie has performed a measurement or not, or if she has performed a measurement, even what she got. You can't use that to send any sort of signal. And so the quantum story, the Copenhagen interpretation would be consistent with relativity in that sense. As far as non-local things, well, that's actually kind of hard. If you try to come up with some sort of a theory of sort of normal realism-based theory with non-local interactions, it actually would be kind of hard to make sure that relativity is still okay, is to the limit that we can test it experimentally. I'm not saying you can't, I'm saying it'd be hard. I really like this one. I think this shows how Bell's theorem works in a way that, and it shows that nature is fundamentally non-local and weird in a way that you could explain it to anyone, your grandmother, and it doesn't really involve bra-cat notation. So now I'm going to go back and splice this back in with the next video, where I will work out the same result and show how to use bra-cat notation and the GHZ state to get the same result. Okay. Let's assume that Emily solved. These states are eigenstates of spin in the z direction. That's why they're labeled with z's. And then the action in the other directions just perform simple flips, maybe up to a rescaling, okay, by a complex number. Okay, so we need to remember that because we're going to use those to understand various measurements. Okay, so now, what about the experiment I described before? Well, the source produces a GHZ state. What's that? Well, that's just names. Green horn inside the nerve. And 1 over root 2, it almost looks familiar. Remember, it's sending out 3 qubits. So it's going to be built out of the tensor product of 3 spin states. So it turns out it's going to be plus z, plus z, plus z for particles 1, 2, and 3, minus, it's a superposition, so they're entangled, minus z, minus z, minus z. It's not too hard to remember. Now, when we had the Bell pair, the anti-correlated Bell pair with the minus sign, that was a singlet, which we made use of that to kind of rotate, choose different bases, the z basis, the x basis, or the theta basis, or the phi basis. And the form of it was invariant. Well, this is not a singlet. Okay, this would transform under a change of basis. So I'm not going to do that rotation. I'm not going to look at arbitrary coordinates. I'm just going to stick with this basis, the z basis, and then I'm just going to look at what happens when we apply Pauli matrices to it. So okay, so what I'm going to do is look at what happens. So when one person applies x to this, well, how can we do that? Well, really what I just want to think about is what if all 3 apply, everybody applies something. So let's just say Emily, the first one, applies x, and the other 2 apply y. And then we have y. So we have one person performing X, one person applying Y, one person applying Y to the GHZ state. And then we look at what we're going to get. And when we multiply the effects of all three, like this, well, remember, this is Emily, this is Marie, and this is Marcus. Emily's action that'll only act on Emily's qubit. Marie's action, or matrix, will only apply to her qubit, and Marcus's matrix will only apply to his qubit. And so that you just kind of handle them factor by factor. So let's think about what happened here. Well, the square root of 2, nothing happens. Emily applied sigma x on the first state. That changes it to a plus, goes to a minus. And then Marie acted on her qubit with a y. That would give a factor of I times the down state. And Marcus also applies y, and so that's going to give another factor of I to the down state. So overall, there are two factors of I, which is a minus 1 out front. Okay, and similarly on the second factor, Emily, her operation only just flips it up. So I've got a minus sign here, and I got Emily's piece that just changed it to a plus z, and then Marie's choice of sigma y acting on her part of the qubit, or her part of the state, is going to give me a minus I, and similarly Marcus's part is going to give him a minus I, so we get a minus I squared. So we know with minus I squared, that's a plus 1. Plus z, plus z, plus z. So what we see is that when you multiply the spins, the value, the result of spin measurements from by all of them on this one state, where it's when there's only one x and the other two are y's, the state comes back the same. There's no change to it, and all this, so the product of spins is going to be plus 1. I'll just say it comes out as plus 1 times GHZ. Okay, so the product of all three results acting on the state come out to plus 1. Okay, so that's how the quantum mechanics will encode this result. There's a little different way. Well, that's what we get. Yeah. And because it comes out back proportional to the original state, you get plus 1 100%. Really, I should say it's plus 1 100% of the time. And so that really closes it off. All right. You could see that by, if you were to remember using our recipe for average values of this operation, you could sandwich this with another GHZ state, in which case you would get plus 1 times 1 when you take the inner product of the GHZ state with itself. All right. Now, what if, on the other hand, everyone applies X? So what about, so now what if all three people apply? in that case, we would have sigma x, sigma x, sigma x, again for Emmeline Marie Marcus, acting on the GHZ state. I already told you the answer. The answer is going to be that you get minus 1 times the original state. But let's see how that comes out. This would equal sigma x, sigma x, sigma x times 1 over the square root of 2 times, and I'm just going to write it out here, I have plus z, plus z, plus z, minus z, minus z, minus z. Sorry, I'm out of room. Okay? Now, sigma x just flips plus to minus with no factors of I. So each of these is just a simple flip on acting on the separate terms. So this is going to go to minus, 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 and this is going to go to plus, 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 but you have the relative minus sign, which means the overall state is going to be backwards. So this is going to equal 1 over root 2 times minus 1 times plus z, plus z, plus z, minus, minus z, minus z, minus z. So the state comes back to itself, but it has a minus sign, and therefore the product of all three, the product of outcomes that all three see is going to be minus 1 when they all three apply x. And that was the result obtained. No, that's the result obtained in the experiment. Okay? So that's the way that quantum mechanics encodes the this 3-qubit experiment. And that part I put in mostly. This part's not really in David Mermin's. I don't think it's in his original paper. Maybe it is. I don't remember. The real point of that paper is the previous discussion, which the part that you could explain to anyone and show them that the nature of reality is fundamentally non-local. So we have an effect, in general, we have an effect on things that happen way far away from us. However, that effect, at least in the quantum mechanical interpretation, that effect is a subtle one, where individually, if I limit myself to measurements I can make right here, I can't see that non-locality, right? So I just see random noise, 50-50 clicks. But and so therefore, even if I do have some effect on a state far away, that person also will just typically see noise, and they won't be able to see if they happen to get a +1 because of the noise or +1 because I had somehow collapsed the wave function. It doesn't matter. They just see +1 or -1, whatever they see. And because of that, they can't look at their results and say anything about what I've done, or if I've done anything, or if I have done anything, what result I found. So no information can be transferred. And that's the way that relativity is compatible, at least special relativity is compatible with quantum theory, ultimately. There's more to that, but that's a big part of what needs to happen. Okay, so that's enough for this. Thanks for watching.